So in this experiment, you're using the spectrometer again, except this time it's got a diffraction grating instead of a prism. There are a few things that are going to be the same as last time, however, at least to begin with. So we've got a light source back here, and we're going to start out using the helium lamp. We will switch to a different light source later. Another thing that's the same is that the first thing you should do is line up your telescope parallel to the collimator, look at the central image, and make sure that it's as bright as possible. And if not, just grab the whole spectrometer and slide it very slightly back and forth until you get a nice bright image for the central image. You are going to need the position of the central image again, so go ahead and put your crosshairs directly on it and take a reading just like before. So now let's talk about what's different when you're using the diffraction grating instead of the prism. So you'll measure the position of the central image, and like before, you're also going to be measuring the position of various spectral lines. However, remember with the prism, the light came in, went into the prism, and it refracted in one direction only. So you just saw spectral lines over here. With the diffraction grating, it's actually diffracting light onto both sides of the central image. So you would see the spectrum over here, you're also going to see it over here. And so, when you want to take a measurement of a spectral line, you're actually going to want to put the crosshairs on the line on this side, take a reading, go over and find the same line on the other side of the central image, and again, put the crosshairs on it and take a reading. And so the position over here for, say, the purple line, minus the central image, should equal the angle for the purple line over here, minus the central image. And that's something you will check, that you're getting approximately the same angle on both sides for the same color of line. Another nice thing about using the diffraction grating is you don't have to find that angle of minimum deviation with this one. You can just go find a line that you're interested in, put the crosshairs on it, take your reading directly, and the only thing that's hard is you got to go and do it on the other side as well. Another thing that's different with the diffraction grating is that it actually creates more than one version of the spectrum. So what I mean is, if I go to the central image and start swinging the telescope sideways, I would see the whole spectrum. It would start with the purple end of the spectrum and eventually get to the red end. But if I kept going past the red line, I would see the purple lines again, just dimmer. That's called our second order spectrum. So you'd see the first order spectrum nice and bright, and then you'd see it again, dimmer, and that would be the second order, and there'd be a third and a fourth order, and so on. We're only going to be taking data off of the first order spectrum. So that means you'd look at all the bright first order lines, and when you get to the red end of the spectrum, just stop. Because you'd see more lines if you kept going, but those are the second order ones, and we're not interested in them. So you look at the first order spectrum only on both sides of the central image. So now let's talk about what we're going to be doing in the first half of this experiment. So we're using helium because we know all of its wavelengths. That was given to us in the Prism Spectrometer lab manual. So the wavelengths are known, and we can find the angles. So we can go find the purple line, take a reading, find it on the other side, take another reading, and as I said, you calculate the angle on both sides. Those two angles should agree with each other with an uncertainty, and if they do, then you'd average them together. And we know that this is the equation governing where all of our wavelengths are going to appear. So the average angle from both sides would be this theta value. We're also studying only the first order lines of the spectrum, so that means n equals 1. So we can simplify the equation to this. So we know what theta is, and we know what the wavelengths of helium are, and so what we're trying to find in this first part of the experiment is d. What is d? Well, the diffraction grating is just a series of very fine lines scored onto a piece of glass, and all the lines are parallel to one another, and d, the quantity we're trying to find, is just the distance between two of the lines. And that'll be a very small distance. It's measured usually in micrometers or nanometers. But we're going to calculate that for each of the spectral lines in helium. That'll give us about 6 different values for d, but of course it's all the same diffraction grating. So they should all agree with each other, and you can just average them together. So in this first part of the experiment, you're getting an experimental value for d, the grating spacing for the diffraction grating. In other words, the distance between two lines that have been etched onto the surface of the glass. In the second half of the experiment, you're going to be identifying an unknown gas. In other words, you're going to actually figure out what its wavelengths are and use that as a fingerprint to identify it. So of course, you're going to need to change the spectral tube. So turn off the lamp, and to pull it out, it's actually spring-loaded, so you can push down and pull out. One thing to be careful about, however, is that these can heat up. So I recommend you handle it up here where the glass is thicker rather than in the center. It does tend to heat up quite a bit there. So you've been given a second spectral lamp with a number on it. So this is your mystery gas, and it's got a code on it. Write that in your notes so that your lab instructor can identify which spectrum tube you were given. And these lights also have the number written on the end of them. So write down this code somewhere in your book. Now, to actually put this in the lamp, as I said, you just grab here where it's a little thicker and a little cooler, push down, and it comes out. So it's on a spring. And then this one, same thing. Push down, pop it in there, and then when you turn this on, you should see a different color because this is a different gas. As before, get this guy lined up and just look through the telescope and wiggle things back and forth until you see a nice bright central image. So the first thing you should do is actually just have a look at your spectrum. So swing off to one side and look at all the first order spectral lines. Take a look at those, and in your book you want to describe what they look like, as well as writing down this code. If there's pencil crayons in the lab, go ahead and draw what you see as well, but definitely describe it in words and write down the code, so that your lab instructor can identify your mystery gas, even if you don't. Next, you're going to want to calculate the wavelengths for all of the major spectral lines in your mystery gas. So you're still using this equation, except now you have a value of D. You got that experimentally in the first half of the experiment with helium. And you can measure the angles the same way you did before by getting the position of each spectral line on both sides, calculating the two angles, averaging them, and plugging that in for your theta value. And that means that you can now calculate the wavelength for each of the spectral lines. Now, everybody's gas is going to have a different number of spectral lines. So if you look through here and you see only 3 spectral lines, you'll get all 3 of those wavelengths. If you see 12, then I'd recommend you choose the 6 brightest ones and take measurements just off of them. So take measurements on 3 to 6 different spectral lines, depending on how many you see. Once you calculate the wavelengths for all of those spectral lines, you'll be given access to the spectrums of a variety of different elements. And based on those spectrums, in comparison to the values that you calculated and what you actually saw through the telescope, you try and identify what your mystery gas was. And just explain your reasoning well.